Hello, my name is Jim Lee, and my topic of my thesis is modeling binary liquid alloy properties with machine learning potentials. And I took a case study for lead lithium alloys. In field of nuclear engineering, liquid metals are proposed as a candidate material for coolant for several types of nuclear reactors. Taking as an example, sodium-cooled fast reactors (SFRs) use liquid sodium as its coolant material since sodium has a suitable melting and boiling point, and it allows it to operate without pressurized vessel tanks. Its high thermal conductivity and heat capacity improves the power generation efficiency as well. And lastly, its low moderating property is able to use the sodium as a fast neutron reactor equivalent. A liquid metal has a corrosion and oxidative feature, and several countermeasures has been discussed. Uh, However, most of the countermeasures have difficulties in practical uses. For example, there are countermeasures against corrosion by forming an oxide layer on the structural materials. However, there are certain conditions that the oxide layers can be maintained stable. However, in the during the unexpected situations like reactor accidents, the oxide layer cannot function and the corrosion will happen. Also for the burning, there are several types of countermeasures, for example, inert gas insertion and then double pipe method. But however, many of these countermeasures increase the complexity of the reactor design and also may not work in extreme cases, and also their feasibility is not proven yet. The, the reason why, uh, the main reason why these countermeasures have such limitations is because the liquid metal still maintains its innate corrosive and oxidative behavior. Therefore, instead of such temporary solutions, we need a fundamental approach to directly control the property of the liquid metals. Currently, known candidates for liquid metals for nuclear engineering, such as lead, sodium, and others, are already known to have these corrosive and oxidative issues. But there is a possibility of finding an unknown alloy with both acceptably low corrosive and oxidative properties, which could intrinsically prevent corrosion and burning. Therefore, we think searching for such ideal liquid alloy is worth of research. Experimentally, in order to in order to in order to measure the property of the liquid alloys, uh, experimentally measuring property can be one way. But however, since there are a significant number of combinations of alloys, it will be physically challenging and time-consuming to screen for most of the alloys in the world. Also, performing Aboriginal calculations can be considered instead, but however, it still requires high computational cost to gain enough accuracy for the screening. Then employing machine learning potentials can solve this as it can achieve accuracy as good as Aboriginal calculations with much lower computational cost. Therefore, we have chosen to build machine learning potentials to calculate properties of liquid metals and construct a large dataset. As a first So therefore, the main objective of this research is to model behavior of lead lithium alloy. And the reason why we chose lead lithium alloy as a test case is because first, it is already a known candidate material for Triton breeder. And then second, there are expectations for interesting features since lead and lithium has uh, chemically different properties. So the goal of the research can be simplified as modeling bialloy behavior with machine learning potentials, and this can be divided by three tasks. First is to build an accurate machine learning potential for lead lithium alloy. Second is to analyze properties of lead lithium alloy across all compositions. And third, analyze behavior of oxygen impurity behavior across all compositions. So in this research, we have used the density function theory, which is a quantum mechanical method that predicts how electrons behave by solving quantum equations. And quantum equations are non-interacting Schrodinger equations. In this research, we used a code named FAST for the DFT calculation. We also used classical modular dynamics. Uh, this simulates atomic motions by solving Newton's equations of motion. And unlike DFT, it requires interatomic potential model to be given to run the simulation. It takes less computational costs than DFT for the most of the times, and then we chose LEMS as our as our code package. For the machine learning potential, the reason why it can achieve the DFT level accuracy with the less computational cost is because the machine learning potentials are fitted into DFT data, and then it is then given to the classical molecular dynamics as interatomic potential model. Several machine learning potential models have been tested to evaluate their performance, and then when comparing with the test error and then computational efficiency error, we concluded that a model called moment tensor potential makes the best compromise. Moment tensor potential, or MTP, is a machine learning interatomic potential that enables accurate and efficient modeling of atomic interactions. It uses datasets from the DFT calculations fitted with the tools like MLIP package. An MTP is a many-body potential based on the moment tensor descriptors. Then this MTP was trained with active learning. Active learning is which helps you to ensure that the trained MTP can accurately describe the entire target system. Active learning automatically selects the new training data by comparing similarity between the new atomic configurations with the existing data set using an indicator called MV-grade. To construct the MTP for the binary lead lithium system across all compositions and a range of temperatures, we used a two-step training method. One consists of supervised learning and followed by active learning. First, in supervised learning, the aim was to make the initial MTP that will be used in the active learning. The training set of the initial MTP was given by a large set of DFT calculations, and for the MTP to cover all compositions in a bit wide range of the temperature, we gave variety of the compositions and the temperature for the tests, DFT calculations that we're going to extract test data. And then for the uh, stability of the MTP, we also gave the variations to the volume and then initial configuration as well. MTP was then generated and then went through active learning. After 2 iterations of active learning, the MTP training was complete, and then in total there were 881 data sets in the training set. We then calculated the mixing enthalpy of the alloy. The mixing enthalpy calculation for the MTP were compared with the previous were compared with the experimental version. The MTP rev, the red line, is the MTP that we have trained, and the other black symbols and then cyan yellow symbols are the experimental results. And then we were able to conclude that our MTP has achieved a level of accuracy that closely matched with the experimental results across the entire composition range on lead lithium alloy. We also calculate the heat capacity, and we were able to notice some deviations from the heat capacity result, experimental heat capacity result. There are possible causes for such disagreement. For example, electric temperature effect may have caused this error, or relativity effect of the lead may have caused this error, or mostly innate error in the exchange current function probably have caused the main part of the error. Then, now coming with the property of the alloy, uh, there are largely two composition regions that is usually under the focus of the study, but however, this is the first as far as I know, this is the first comprehensive analysis across the full composition range so far. And since the behavior is different for each compositions, we divided the composition by 3 intervals. And in this presentation, I will focus on one of them. In interval A, we calculated the RDF, the radial distribution function, for the lead, lithium, and lithium interactions. And we found out that the average distance between lead and lead is way much longer than lead lithium or lithium lithium. And this indicates that the lead atoms were surrounded by lithium atoms for the most of the time. And we also noted that there is a linear trend in mixing enthalpy curve and then lead number ratio, indicating that proportional increase of the uh, decrease of the increase of the lead content leads to the proportional decrease of the enthalpy. We calculated the coordination number, and then we were able to notice that from 0% to 20% lead, which is interval A, we were not able to find any change in the coordination number. And this indicates that lead-lithium interaction in this region is not uh, changing, but rather maintained so far, even if the number of the lead increases in the system. And now I'm going to explain about how we have calculated the oxygen solution enthalpy with our MTP. We have trained an oxygen solution. We have trained an MTP that can cover the oxygen impurity behavior in lead lithium alloy, and we have calculated the oxygen solution enthalpy for the all range of calculations. Right at the right figure, the lower black dashed line indicates the oxygen solution enthalpy of the lithium, and the upper dashed black line indicates the oxygen solution enthalpy of the lead. And the red line indicates the solution enthalpy by compositions. And we were able to notice that the solution enthalpy was changing as the composition of the alloy has changed. And this is meaningful because our target, which is a new alloy that has acceptable corrosivity and an acceptable oxidativeness, can be achieved by changing the composition of the alloy. We wanted to know why exactly this can happen. Also, we were able to notice that even in the lead-rich regions, the oxygen solution enthalpy was still closer to the pure lithium ones, and we wanted to know why. So that's why we performed the oxygen solution and we performed the RDF calculation for the oxygen atom inside of the alloy. And the RDF result indicated that the oxygen lithium distance for in liquid pure lithium and eutectic were similar, even if the eutectic had 83% lead inside of the system. And this suggests that lithium maintains the structure with the oxygen despite of higher lead content. So we calculated the coordination number of the oxygen with lithium, and we're able to find out that the trend of the decrease of the coordination number and the solution and absolute value of the solution enthalpy was quite similar. And this supports the conclusion that the local oxygen lithium structure dominates the solution enthalpy. And it is attributed to the larger electronegativity difference between lithium and between lithium and oxygen compared to the lead and oxygen. We then performed Bethe charge analysis, which tells how the charges are transferred between the atoms. And then we were able to find out that at the large lead-rich region, the oxygen charge was lower than lead, which means that there are strong Coulomb interactions with lithium and oxygen. And this would probably be able to maintain the lithium-oxygen bonding structure. For the lithium case, in the lithium-rich region, there are some regions where lead charge was lower than oxygen, but in this case, the abundant lithium prevents the competition to form the structure with the lithium. So therefore, the oxygen lithium structure was preserved in this region. So the objective of this study was to construct the MTP for the binary alloy system. The first task was to build an accurate machine learning potential model for the lead lithium alloy, and we trained the lead lithium alloy modeling MTP, and then we have validated its performance by comparing with solution enthalpy and then mixing enthalpy and then heat capacity results. We then analyzed some properties and mechanism behind the lithium alloy, and we were able to find out that there are some compositions, structures, atomic structures inside there, and the charge transfer were identified as key factors that determines the mixing enthalpy. Lastly, we analyzed the behavior of the oxygen impurity across all compositions, and oxygen solution enthalpy was calculated for all range compositions, and then shift of the oxygen solution enthalpy by a change in alloy was observed. And finally, local structure of the lithium alloy was identified to play a key role in determining the oxygen solution enthalpy. So this is the end of my presentation, and thank you for listening.